One of the reasons that the given test cases are insufficient is because they do not cover all paths through the method. There are 4 paths going through this method, corresponding to each distinct combination of the conditions in the code. If both conditions are true, then 0 is returned. If only condition 1 is true, then 1 is returned. If only condition 2 is true, then -1 is returned. And if both conditions are false, then 0 is returned. Okay, if this is the case, then why don't code coverage tools test for covering all possible paths instead of just all possible statements and branches? Well, because even with if statements, the number of paths can get quite large. And when we add loops to the problem, it quickly becomes intractable. Consider what would happen if we had a program flow that looked like this, where the dark black line is part of a loop that can iterate no more than 20 times. I'm going to show you just one possible path through the code. Okay, this path goes through the loop and all conditions inside are true, and then the code goes through the loop again and takes a different path this time. And then the code goes through the loop yet again one last time and takes a different path again. This entire line that shows the execution going through the loop 3 times and taking 3 different paths, this line represents a single path of execution. So, given that what we just saw is only one path, how many paths exist through this code? The answer is a lot. There are 10 to the 14 possible paths through this code. If we tested one path per millisecond, it would take 3,170 years to cover all the paths. This is why covering all possible paths, which is often referred to as exhaustive testing, is not something that is practical to do. So, if paths are created by conditions, a program with no conditions has only one path. Given this fact, you may be able to answer the following question. Is it possible to write tests that cover every single path through the code and still have incorrect code? Please pause the video and see if you can answer this question. Ready? Well, you certainly can write tests that cover every path and still have incorrect code. And the next slide gives an example of this. Here's a method with a single statement. Its specification says that the result returned from this method is equal to the sum of the 2 arguments. Since this method does not have any conditions, it only has one path. Therefore, any test case for this method will cover that path. In this case, we're testing that the sum of 3 and 4 equals 7. And this does indeed pass. However, there do exist integers which will not pass this test case. Can you think of what they might be if I give you 10 seconds starting from now? Well, one pair of integers would be maxint and maxint. You're not going to get the result that is their sum. You will get a valid integer, but it won't be the integer you're looking for. Try it for yourself and see. So, even so-called exhaustive testing will not cover all possibilities. In fact, the only way we can be sure to cover all possibilities is to test every single combination of input values. Of course, just as testing all pass through a program is impractical, testing all combinations of input values is also impractical. For white box testing, 100% statement coverage plus 100% branch coverage is usually the ideal that developers try to aim for, and even this is often unrealistic. So let's turn our attention from code coverage and look at how to design a practical black box test plan. Here's a square root method that takes two floats. One is the number you want the square root for, and the other is the accuracy bound on the result. The specification for this function has a precondition that says n must be greater than or equal to 0, and the accuracy must be strictly greater than 0. The postcondition says that the result is between n minus accuracy and n plus accuracy. Since this is black box testing, we're going to ignore the implementation and look only to the specification for our test cases. The first thing we'll do is create a range diagram for our two inputs and our one output. When we have a well-defined range of inputs and outputs, as we do here, the endpoints of those ranges are boundary points that we can use in our test cases. In addition to these boundary points, I claim that there is at least one more boundary point for the number input, and that is 1.0. Why is 1 a boundary point? Well, we're looking at a square root function, and there's something interesting that happens to the square root of a number at 1. First, the square root of 1 is 1 itself, so that is certainly interesting. But we can say something about the square root of numbers less than 1 versus the square root of numbers greater than 1. If you're not sure, take 10 seconds to try and figure out the distinction, starting now. Ready? The easiest way to see the distinction is by looking at a perfect square that's greater than 1 and then looking at its reciprocal, or 1 over that number, because that number is less than 1 and it's also a perfect square. So let's take 4 and 1/4. The square root of 4 is 2, and the square root of 1/4 is 1/2. If you plot these points on a number line, you will see that 2 is less than 4, but 1/2 is greater than 1/4. And this is the case in general. The square root of a number that is greater than 1 is always less than the original number. And the square root of a number that is less than 1 is always greater than the original number. So 1 is definitely a boundary point. Okay, let's pick a few test points. Notice that these test points tend to be around the boundary values. The next slide gives a rationale for choosing each of these points. The first 3 points, A through C, are for n, the number that we want the square root of. The next 2 points, D and E, are for accuracy, and the last 2 points, F and G, are for the results. Points A through C are points that are near the boundary points in the range diagram for n. Points D and E are just chosen because they're 2 different accuracy values. You might want to choose something like max value for this just to see if it works, but in this case we didn't. Finally, points F and G are chosen as the endpoints of the range for the result. Once we have our points, we can try to arrange them into a test plan. Here we have 3 test cases that collectively use all of our points. The table here gives the specific input values and it gives the expected output as a range. And that's a quick example of how you might come up with test cases when you only have access to the specification. We're going to revisit these test cases in the next video, which talks about flow graphs.